In this video lesson, we're going to talk about solution stoichiometry problems. In order to do this lesson, you should have a copy of handout, solution stoichiometry, that you would have gotten in class or you've printed off for yourself. So solution stoichiometry is basically using exactly the same type of math we've been doing in other stoichiometric problems, except now we're going to be looking at using the mass, volume, or concentration of the product to determine the molar concentration of a reactant, or vice versa. So basically, we are using a mole ratio, and we're using the molar concentration as a conversion factor to go between volume and concentrations of reactants and products. So these types of problems have the same general strategy. We start with the volume or concentration, and then we use the other numbers. So if we have volume, then we use the concentration to calculate number of moles. We then use a mole ratio to calculate another amount of moles. And then we take that number of moles and we use that to calculate the volume and concentration, of what we're looking for. So our general strategy for solution stoichiometry is we start with volume or concentration, calculate moles using whatever one of these, the other one of these, use a ratio to get the other amount of moles, and then use volume or concentration to get the opposite, or what we're looking for. So in our first example down here on your handout, we want to calculate the volume of 14.8 mole per liter of NH3 that is needed to react completely with 1.0 liters of 12.9 mole per liter phosphoric acid to produce NH3 bracket 2 HPO4 aqueous. The first thing we need to do is write out our balanced chemical equation. If we do that, we end up with 2 NH3 plus H3PO4 reacts to produce 1 NH4 2HPO4. The next thing we want to do is we want to write out our givens. So there's a nice neat way we can do this. To make it a little bit easier on yourself, you can just write your givens directly under your equation. So we're going to start with V. We are looking for our volume of 14.8 mole per liter NH3. So that means that we're looking for a volume of NH3. But we have a concentration of 14.8 mole per liter. For H3PO4, we have a volume right here, 1.0 liters, and our concentration is 12.9 mole per liter. So to do this problem, you want to set yourself up with your strategy line again. So basically, you have all the information for H3PO4. So you have a volume of H3PO4 and you have a concentration for H3PO4. So you can very easily calculate the number of moles of H3PO4. So you're going to start with your strategy. It's going to be the volume of H3PO4. You're going to calculate the moles of H3PO4 using concentration. Then you're going to use a mole ratio from the equation to get the moles of NH3. And then you have the concentration of NH3, so therefore you can calculate the volume of NH3. So then just set up your factor label method equation. So we are looking for volume of NH3. We are starting with the volume of HPO4. So 1.0 liters of H3PO4 We're going to multiply that volume by its concentration. We want to end up with moles, so 12.9 mole goes on the top. And 1 liter of H3PO4 comes on the bottom. We get our mole ratio from the periodic table. We have moles of H3PO4 right here. So we want to cancel that out by putting the moles of H3PO4 on the bottom. And according to our balanced chemical equation, there's only one. So we'll have 1 mole of H3PO4 reacts with 2 moles of NH3. So if you stop now, you've calculated the number of moles of NH3, but the question is asking us for the volume of NH3. So because you have the concentration, you can easily calculate that. The concentration is 14.8 mole per liter. So we have moles right here. So to get rid of that, we're going to put moles on the bottom. 14.8 moles. And that's in 1 liter of NH3. So you've punched it into your calculator using brackets again. So brackets around anything like this. You end up with an answer of 1.7432 liters. And if you do a quick unit check, you will see that your units all cancel out. You have liters phosphoric acid here, canceled out here. Moles of phosphoric acid cancels out here. Moles of NH3, moles of NH3 leaves you with liters of NH3, which is exactly what you're looking for. And then a quick significant digits check tells you that you can only have 2 significant digits because there's only 2 digits up here. So your answer gets rounded to 1.7 liters of NH3. So then we would finish off with our therefore statement. The volume needed is 1.7 liters of NH3. So when you have that done, flip your page over, press unpause, and let's take a look at example 2. In this example, we have a 10 milliliter sample of sulfuric acid reacts completely with 15.9 milliliters of 0.150 mole per liter of potassium hydroxide solution. We want to know what the molar concentration of the sulfuric acid is, and we have a balanced chemical equation. So the first thing we want to do is pull out our given information from the word problem. Once again, you want to write your volume and your concentrations underneath your equation, just to make it nice and easy and tidy. Okay, so we have our givens right here, pulled from our word problem. Looking at our givens and the word problem, we know we are looking to solve for the concentration of H2SO4. So when you're setting up your strategy, that belongs over here, concentration of H2SO4. That's what we're looking for. We know with stoichiometry, there's always a mole ratio in the middle. So we know to get to that concentration, we are going to have to calculate the number of moles of H2SO4. And we also know that we have to get the number of moles of H2SO4, we're going to have to calculate the number of moles of KOH and use a ratio. And then to get the number of moles of KOH, we're going to start with the volume of KOH, and we're going to use the concentration to get there. And over here, to get the concentration of the sulfuric acid, we're going to use the volume of sulfuric acid. So we're looking for the concentration of H2SO4. We're going to start with our volume of KOH. So we have 15.9 milliliters of KOH. We're going to convert that to moles using our concentration of 0.50 mole KOH over 1 liter of KOH. We're then going to convert the number of moles of potassium hydroxide to moles of sulfuric acid using our mole ratio. We have 2 moles of KOH to 1 mole of H2SO4, and then we'll finish by converting that moles to a concentration. We just take our volume of 10 mils. I'm just going to squeeze in H2SO4 here, and we just put it under 1. So often we ask, do we have to convert our units, our volume units here to liters? The answer is no, because this mil here is going to cancel out this mil here. And it leaves us, once we look at all of our other units, our mole of KOH, our mole of KOH gets canceled out, and it leaves us with the units we're still looking for, mole per liter. So we punch this into our calculator using our brackets. We get 0.11925 mole per liter. Quick look at significant digits tells us that we can only have 3, so we end up rounding to 0.119 mole per liter, and that's our concentration of H2SO4. So we write ourselves a nice therefore statement. So therefore, the concentration of sulfuric acid is 0.119 moles per liter. So make sure you have this copied down. This is the end of our lesson on solution stoichiometry. If you want to get ahead of the game, try some of this practice before you come to class. If not, I'll give you a little bit of time to do this in class coming up. And I will see you next time.